what is it that I discussed last time? Do you remember?
SO2 and being a subgroup of SP.
Huh? What?
Number of compact generators.
Okay. Yes. Okay. So, yeah, so what I said is that if I take this group sp2n r, which is the group of 2n cross 2n real matrices satisfying this condition, that S omega S transpose is equal to S. Okay. So, then so this group has, so basically in order to parameterize this group, you need n into 2n plus 1 real parameters, right. These independent, this many independent parameters you will require to specify any element S of this group. I mean, remember this has 4n square elements, right, each group element, but because it satisfies this condition, you can figure out that. So, how will you figure out that this many parameters? So, this is the number of independent parameters required to specify any element of this group. Okay. So, what you can do, you can just just look at the number of conditions here and figure out that this is the number. Okay. So, for example, for n is equal to 1, this is what? This is 3, right. Okay. Oh, sorry, this is not S, this is omega. Yeah, omega. Yeah. So, how will you figure out that this many real parameters are required, which is of course much less than 4n square. I agree. And basically this is the reason that I said that this group has this n square number of compact generators, which are of the form like like you can say 1 upon 4 aj dagger aj plus aj dagger, j is equal to 1 2 3 up to n. Then you have 1 upon 4 aj dagger ak plus ak aj dagger, something like that. This is for j and k is equal to 1 2 3 up to n with j less than k. So, this number is n into n minus 1 by 2, this number is n, this number is n into n minus 1 by 2, and then iota by 4 aj dagger ak minus ak aj dagger. This is again they will satisfy the same condition, right. So, these are compact generators and total number is, what should be the total number? N square. This is n, this is n into n minus 1 by 2, here also you will have n into n minus 1 by 2. So, the total number is n square. This is the total number of generators. Okay. And this forms the, so therefore, this will generate the maximal compact subgroup. And what is that maximal compact subgroup? Basically, this is your subgroup which is u of n. Okay. The group of n by n unitary matrices, and how many generators it will have? N square. Okay. If it is SUN, then the generators will be n square minus 1 because of the determinant condition, but here it is n square. Okay. So, this is the group having generators n square, which is generated by this basically the n square number of generators, and this is of course a compact group. Okay. So, you see that U n is a compact subgroup of this group sp2nr, right. I mean, you might say that this is 2n by 2n matrices and this is n by n matrices. Question is not that. When you talk about group, I mean this should be independent of representations. Okay. So, so this can work in any dimension, it does not matter. So, basically this you can consider as generators of this group, and of course, these are also generators of this group. Okay. And the remaining generators, these are the non compact generators which I mentioned earlier, and which are n into 2n plus 1 minus n square, which is basically n into n plus 1, and which you can think of like 1 upon 4, this should be like something like this, a j dagger a k dagger plus a j a k, with j and k is equal to 1, 2, 3 up to n, and j less than equal to k, because for single mode system this will give rise to squeezing, and this is what is the number n into n plus 1 by 2, and also you will have iota by 4 a j dagger a k dagger minus a j a k. See, these are basically rotated version, you can go to a rotated phase space operator, and again the same thing. So, if the number is again n into n plus 1 by 2. So, as a whole this gives rise to n into n plus 1 number of generators, and these are the non compact generators.
So, in the first case, okay.
Yeah.
I saw that you have written hash n square, but it should you have actually written hash n.
Which one is hash n square? Total.
That's total. This
Yeah.
also sum up to.
Yeah, because this is n,
Okay.
this is n into n minus 1. So, it will add up to n square, and this will add up to n into n plus 1. Okay. Right. Okay. So, now we have already noticed that if I take an S which is a 2n cross 2n orthogonal, I mean real orthogonal matrices, real orthogonal matrix with determinant of S is equal to 1. So, this means that S is an element of this SO2n, right. Okay. The rotation group in 2n dimension. So, if this is the case, then we know that this is not necessarily it belongs to sp2nr. In other words, not every rotation gives rise to a canonical transformation. Okay. So, this you can, so this only exception is n is equal to 1 case, but if you go higher values of n, then so basically this is not this in general. Okay. Now, why this is important? Because you see that we have considered this Williamson's theorem, Williamson's canonical form, where we want to see that if I take a symplectic transformation S and then I apply it on a covariance matrix and then I apply this transpose. So, this in principle I can figure out a symplectic transformation. So, that this will become kappa 1. Now, I have used the permuted version. So, let me write it like this kappa n, then kappa 1, kappa 2, kappa n. So, here my notation is that this is x 1, x 2, x n, then p 1, p n. Okay. So, just a permuted version. So, this is what Williamson's theorem tells me for some S belonging to S p to n r, provided this is a this is a real symmetric positive definite matrix and all that, okay, which satisfies this condition that gamma plus iota by 2 sigma greater than equal to 0. Right. Now, the problem is, because this S is a symplectic transformation, it is not necessarily an orthogonal transformation, and therefore, I cannot claim that these are eigenvalues of this gamma. So, what we should look for is those symplectic transformations which corresponds to rotation, because here the because we are dealing with real matrices, instead of unitary we will have to look for the rotations. So, we should look for the rotation matrices. So, that means elements of SO2n which can also bring it into this form, right. Unfortunately, we cannot look for arbitrary S, because that will not work, because that is not a symplectic transformation. So, what we should look for is this one, those elements which lies in the intersection of okay. So, those rotations which are also symplectic transformations. So, this is what we should look for, and if we can manage to figure out, that will be really good.
So, we actually need only one S, right?
One S. Yes, 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 yes. Yeah. Yes. And now, if we count this thing, so SO, SO n, for example, any n. So, this is a, how many generators you will have? N into n minus 1 by 2 for SO n. How? For example, you can take as its generators, that means the Hamiltonian, these kind of Hermitian operators, like something like, well, these are not necessarily Hermitian operators, I mean these are anti-Hermitian. So, anyway, so its generators you can take it to be something like this. So, these are the matrices, this is your diagonal. So, somewhere you take 1 and here in the reflected version you take minus 1, everywhere else 0, okay, right. So, if we take, so for example, if I take say n is equal to 3, so then these are the generators like 0, 1, let us say minus 1, 0, and then 0, 0, 0, 0, 0. This is 1, then this is 0, 0, 1, then 0, 0, 0, then minus 1, 0, 0, okay. And the third one is like 0, 0, 0, 1, no, not 1, what is that, 0, 0, 1, and then 0, minus 1, 0, okay. So, these are the 3 generators of the group SO3. Okay. I mean this you can take like S x, S y, S z, I mean with some factor, but that is okay. Is not it?
How are we sure that this intersection is finite?
Which intersection? Intersection is not finite, it need not be finite, in fact it is infinite, but the question is
Non-zero.
yeah, right.
There exists one S which is rotational and also
Yes. So, like this we have given so many examples, like in 2 dimension we have given example, this can be done in higher dimension also. So, any okay. So, basically what you can figure out for given any dimension, a rotation matrix can also become. So, basically rotation in this case like yeah. So, basically what my point is that if you take this as your generators of rotations, any rotation matrix generated by this will always be an element of sp2nr. Okay. Because these are also these are also generators of sp2nr, right. So, therefore, this is automatically and yeah. So, this is actually non-empty, right. So, as a result yeah. So, point is that not arbitrary element of this will be a symplectic transformation, but an element of this which is generated by some of these generators will be automatically element of this. Yes, yeah, right. This you can see that they will of course generate this. I mean these are not Hermitian, but you can make them Hermitian by multiplying iota or something like that. So, then this will be your generators of the SO3. Okay. And if you look at this, n is equal to 3 means this is again this is total number is 3. For n is equal to 2 it should be 1. Okay. Right. Anyway, so this is the number of generators. So, as a result for SON, so number of generators of SO2n, this is 2n into 2n minus 1 by 2, which is n into 2n minus 1. This is the number of generators. While for SP 2nr, I mean number of generators of SP2nr is n into 2n plus 1. But still of course, as I said, not every element of these is a symplectic transformation. So, it is not. So, SO2n is not a subgroup of SP2nr, they have some overlap. Okay. Right. So, now I told you some time back that because we are dealing with quadratic Hamiltonian. So, if I look for a covariance matrix whose jth entry is less than half for some j, then we say that this corresponds to squeezing. Okay. But this is for specific observations that we have made, like if you take a like in the case of single mode, or even if you go to specific cases like if it is a diagonal form, then also it follows, because this will give rise to a thermal state. So, now what we want to do is to make this statement very general. So, we want to make the statement about squeezing in a way which is okay. So, which is called, so let me call this as this group as, I mean this let me call it as K n. Okay. This is my notation. So, then what I am looking for is statement of squeezing. So, squeezing, quadratic squeezing in K n invariant form. What does it mean? It means that I will apply all possible symplectic transformations allowed by this set to bring my covariance matrix in a form where I do not have any problem in stating about the squeezing. Okay. So, this is what we are going to do now. So, a statement about squeezing in K n invariant form, and so as I mentioned, we mentioned about we discussed about squeezing without this rotation, right, because we took a single mode squeezing like something like this, some maybe r by 4 a dagger square minus a square, right, something like that. I also said that you can do a rotation, right, in the xp plane, but generically in higher dimension what we want is a similar statement, but so that it can become this K n invariant. Okay. So, I will tell you what does it mean, this K n invariant form. So, for that what we are looking for is a structure of K n, which is SO 2 n intersection SP 2 n r. So, what is the structure of this? Okay. So, let us take this transformation S r because we are dealing with real matrices. If you do not want that, you can just mention S of x and y, and this is your x, y, minus y and x, where this x and y, these are n by n real matrices. Okay. Right. So, therefore, this is a 2 n by 2 n real matrix. Okay. Right. Now, let us see what is this x y and then S of x y transpose. What is this? This is x y minus y x, and this will be x transpose minus y transpose, then y transpose x transpose, and this will be your x y transpose x transpose plus y transpose, and this entry is minus x y transpose plus y x transpose. This one is minus y x transpose plus x y transpose, and this is y transpose plus x transpose. Is that clear? Okay. Right. Yes. So, what I want is this matrix should be orthogonal, because I want it to be an element of SO 2 n. I also want it to be an element of SP 2 n r, but let me first demand this to be an element of SO 2 n. So, then this has to be equal to identity, this is n by n, this is 0 n by n, this is 0 n by n, this is identity n by n, right. And what does it mean? It means that that x transpose plus y transpose is equal to identity, and what else? X y transpose is equal to y x transpose, right? These are the two things you get, isn't it? Okay. Now, let us demand that okay. So, what about S x comma y, then omega, and then S x comma y transpose, to see whether this will equal to be omega. So, this is x y minus y, then x, and then omega is what is that? 0, this is n by n, identity n by n, minus identity n by n, and 0 n by n, right. And this is again x transpose minus y transpose x transpose.
So this omega is defined to be
This matrix, this is my omega. This is the canonical.
skew matrix.
Huh?
Any what is it called? Skew and what matrix is this called?
No, this is a
Does it have to be identity like kind of thing or any?
no. This is actually, this is the matrix for omega. Because this satisfies this commutation relation. It comes from here, like. Sorry, what?
I mean, now we have changed all the x's are together and p's are different, no? And that will change this thing, no?
No, I didn't get. What is your point?
Like the rj,
Ah,
all the q's are together and then p's are together, right?
yes,
Then does it change this?
It's already in the changed form.
Change
yes. It is already in the change form. Yes, yes. Right, because I have written this first, this x1 x2 xn, and then y1 p1 p2 pn, right. So, the first one, this is of course 0, right. The commutation between xi and xj, commutation between pi and pj, this will be also 0. Now, commutation between xi and pj, this is 1, and commutation between pi and xj. So, this has to be the case, okay, right. Yeah. So, now can you tell me what will be this?
So it will be y yt xt. This next one.
Hmm?
First element. You are asking for the whole thing.
Yeah, whole thing. Yes, yes.
I was first multiplying the second and third.
Okay, second and third. Okay, so that means this is x y minus y x, and this one
So it will be yt and then xt
xt
and then xt minus yt.
minus xt, right,
Oh sorry,
minus
minus
xt
and yt.
yt, right, and this will be, so x y transpose minus y x transpose, and then it is x transpose plus y transpose, and this one is minus y transpose minus x transpose, and this is minus y x transpose plus x y transpose. So, if I now use this formula, these rules, then this will be basically this one, right. Oh no, sorry, this will be what? 0 identity minus identity 0, isn't it? Okay, and this is basically your omega. So, you see that once I take this matrix to be an element of SO2n, it automatically becomes an element of sp2nr, right. And so,
So there is a proper subset.
which one is proper subset?
So any element of SO2n
Yes,
will be element of S. No, that you said is not possible.
Not any element, just any.
this is a special kind of element.
Oh, of this form. Any
Yes.
element of this form will give you.
Yes, yes. Okay. So, therefore, this Sxy, this is an element of Kn. Right, provided it satisfies this condition, of course, that has to be the case, right. You can also prove the converse. So, the converse is, if I take any element of this Kn, it can always be cast in this form.
Well, this is the more general intersection.
Yes. So, the converse you can, I am not going to prove this, you can try to prove that if I take any element of Kn, any element of Kn means it should be an element of SO2n, and at the same time it should be an element of sp2nr. If you take that into account, then you can prove that that element must be of this form. Of this form means, of course, it should satisfy this, otherwise it does not make sense, Okay. So, what does it mean? It means that, so therefore, the converse is also true. So, try to prove the converse. Okay. Somebody told me that in the class you should give some homework, otherwise people will not be interested. Okay. So, I said okay, good, I will do that. Some of the people who are attending this course. Okay. So, try to prove that any element S belonging to Kn is always of the form S x y with this condition, what I said, x transpose plus y transpose is equal to identity, and x y transpose is equal to y x transpose. Okay. Okay, good. So, therefore, what we have seen is that this Kn is basically the set of all such matrices Sxy, I mean such that, of course, x transpose plus y transpose is equal to identity, and xy transpose is equal to y x transpose. Okay. So, this is the and which is of course of this form, that x y minus y x, right. Okay. Good. So, you see that what rotations, and this is maximum that you can talk about rotations. So, what rotations also become symplectic transformations? These are the rotations. Okay. So, any element of these will be rotation element, in these are elements of SO2n, at the same time they are also symplectic transformations. Okay. Nothing more, nothing less. Okay. So, if we apply as a symplectic transformation any element of this from this set, right, and if this can bring a covariance matrix in this diagonal form, what I said kappa 2 kappa n, then kappa 1 kappa 2 kappa n, if that is possible, then that will serve my purpose, right. I mean, of course,
Is setting y to 0 and x to identity will satisfy this condition, right?
setting y to 0 and x to identity. Yes, yes,
But that's not a useful symplectic.
and this is just identity matrix.
So, but then it will not diagonalize the covariance matrix.
Any identity matrix is not this is a trivial one,
But I was thinking that that will diagonalize up to this gamma.
No, not always. I said that if we can manage to get some S such that the covariance matrix is diagonalized, then you know that these are basically eigenvalues of this gamma.
So, let us say I want to diagonalize given I have a covariance matrix, I want to diagonalize this. So, this is this a generator or the element of that S, symplectic S?
This is an element of this set K n. Okay, this is an element of this set K n.
Which will give me a symplectic S.
This is a symplectic transformation, no doubt, because this is an element of SP2NR also.
Let us say given gamma I want to diagonalize.
Yes.
That this RHS will give me the eigenvalues for this gamma, right?
So, how do you want to diagonalize this gamma? Gamma is a real symmetric positive definite matrix.
So, I want
So,
to S gamma S transpose.
yeah, so you can of course diagonalize it by a generic rotation, okay, a generic element of SO2n, but that is not what we are looking for, because that may not be a valid symplectic transformation. Okay.
So, one of those rotations will give us the diagonal. Okay, not all.
Not all.
Okay.
Yes. Right. Okay. Yeah. So therefore, what we need to look at is some sort of invariance of this covariance matrix under the action of this set, entries from this set, elements from this set. Okay. Right. Okay. So let us see, I mean, so first of all what we figured out is that any element of K n is of this form. This is our first observation. Okay. Now, let us see that how does it act on, let us say, a generic unit vector in 2n dimensional phase space. Okay. And why do I want to look at it? It will become clear. Okay. So, why do I want to look at it? Okay, good. So, let us take so I am dealing with 2n dimensional phase space, right. So, therefore, so let me take the unit sphere in 2n dimensional phase space, which we call, we know that this is 2n minus 1, S 2n minus 1, right. Like in 3 dimension your unit sphere is S 2, right. So, this is S 2n minus 1, and S 2n minus 1 are the set of vectors x belonging to R 2n such that, now these are column vectors. Okay, so maybe I will write it like this. So, this is x 1, x 2, x 2n transpose such that x. So, this is column. So, this is row x is equal to 1 and this is an element of R 2 n. Okay. So, this is the unit sphere in 2 n dimension, right. Okay. And you can take a basis which is something like this E mu, where this is 0 0 0 1 0 0 transpose. So, this is in the muth position. So, this is in R 2 n, right. This is a unit vector and mu is equal to 1 to twice n, right. This is a basis. Okay. So, what I want is, so what is the action of, so the action of SO 2 n on S 2 n minus 1. How does it work? I choose any element from this and I apply here. How does it work? So, it takes a point of this to another point of this, right, okay, and vice versa. Given any point of this, I can figure out an element of this and another point in this, right. So, basically it says that, you know, if I take x and y belonging to S 2 n minus 1, then, so this implies that y is equal to some s acting on x or some s belonging to SO 2 n. Do you agree with me? And this is unique. So, this is why what we call as transitive action. So, SO 2 n acts transitively on S 2 n minus 1. Transitive in the sense that I take, like I take any point of S 2 n minus 1 and then and any 2 points, let us say x and y, then I can get an element of SO 2 n which will bring x into y, and this is unique. Okay. So, this is transitive action. So, in other words, if I apply, if I take this E mu, this unit vector, and apply all elements. Okay. So, if I take these vectors such that S belongs to SO 2 n. So, I consider all such vectors, this should be equal to S 2 n minus 1. Do you agree with me or not? This is my unit vector, choose any fixed mu, no problem. So, this transitive action means that, I mean, the orbit of this E mu should be the entire S 2 n minus 1.
Orbit, what do you mean by orbit?
So, orbit means, you know, basically trajectory, you know, see, you start from some point and then you keep on applying the group elements, right. Different group elements will bring this initial point to another point, right. So, in this way you can cover the entire set.
So, basically given any input you can map it to any any output. Any element in the domain you can rearrange to map to any element in the domain
Yes.
itself, like
Yes.
in the set itself.
Yes. So, this is basically this is the meaning of the orbit. So,
Just say surface of that 2n minus 1 dimension, right?
this is the sphere in 2 n dimension, unit sphere in 2 n dimension.
But this map will just a surface, right?
Surface there.
Yeah, because you know this will not change the norm, right.
Yeah.
So, it will remain unit vector. So, if I vary this S, I will cover the entire surface. but unfortunately we do not have access to all of this, because not all of these are symplectic transformations. So, it will be better to see whether similar transitive action happens for elements from K n. Okay? If that happens, then we are happy, we can then proceed. Okay. So, now let us take an element from this K n, and this we know that therefore, S should be equal to S of x comma y, which is of this form x y minus y x, and of course, this x transpose plus y transpose is equal to identity, x y transpose is equal to y x transpose. This is fine. Now, let us say that, see, this is the symplectic transformation. Let us say it acts on this thing x1, x2, xn, then p1, p2, pn, right. Let us assume that so this x, so this will go to something like this, right, x1 prime, x2 prime, pn prime, right. This is what it happens under the symplectic transformation. So, let us assume that here let us say this xj prime, this is equal to xj. What does it mean? It means that under this action of such a symplectic transformation, the jth quadrature, position quadrature does not change. It can happen, right? And when can it happen? What should be the form of x and y in that case? Any idea?
So if it's diagonal, only diagonal element 1 is there, other in that row, whatever it's called, only 1 is it's diagonal, other elements are 0. And that's one possibility.
Yeah. So, let us say that, let me take this x. So, this is n by n matrix, right. So, let us say that it's so this is the jth row. So, jth row, and what should happen to this? Jth row should be this, it should be 1, right,
Position.
in the j position, right. So, this is j position, and rest of them should be 0, right.
I think for the horizontal part.
No, even vertical part, no.
I mean, I don't see why that's necessary.
Oh, okay. So, let's not take that. I mean, this is basically okay. So, this is at the jth row, jth column, you have this entry 1.
But then for P also, it should be like that. Oh, sorry, Y. Sorry, Y. The Y element should also have similar conditions.
Why?
Because Y, if you write Y, then its jth element also should be jth row should be 0.
Okay. So, is this clear that this will not change xj, right? This is clear, right? Okay.
No, I mean, not. We need one more condition for Y also. We need condition. This condition.
Why?
That Y element will also can potentially change
No, y, see, this is for all these x, xj's, and this is for pj's. This similarly, this is for xj's, and this is for pj's.
So as a whole, this is a matrix multiplication. So
Yeah, that is true.
the jth row of y should also be 0, fully 0, not even a single one there, because then it can map some p element values to xj.
Okay. So if this is x, then what you are saying, so jth also, here also, so everything should be 0, right? Then only we will get this.
I mean, this is not the most general case, but this will ensure that we get.
Yeah, I am talking about, yes, yeah, I mean this is enough for me. Okay, I am not talking about the most general case. Okay, now this is fine. Now if I look at, now what will happen to pj then under this transformation? What will happen to pj? It will also not change, right? Why?
Same thing will happen, not just j.
Because x, here also you have xj, right? So therefore here if you look at this pj prime, this will be pj, right? So you see that if I consider an element S, okay, so maybe I'll take the unitary representation because that will be easier. Unitary representation xj us the dagger. Not just this happens, you should also have they should happen simultaneously, right? Okay, so right, is this clear? So there is something called stability subgroup. So stability subgroup of a group is, I mean, these are the this is a subgroup under which a particular element or particular vector, whatever you are talking about, it should remain unchanged, right. So you see that I mean you can, and these are allowed, right. I think these are allowed, right. If I take x and y of this form, are these not allowed? I mean, do they violate this condition?
So we can for 2 cross 2 we can say take x as sigma z
Mm.
and y as sigma vector.
Those conditions are satisfied.
Satisfied, right? Yes. So yeah, so this I think it can I mean such s x y we can take, right. Okay. So the basic thing is therefore that the stability subgroup of K n. So where I am fixing these two entries, okay, because as I said, if you fix this, this is automatically fixed and vice versa. You cannot just fix one of them. Okay. So the stability subgroup of this is, what is it? So you have this 2n dimensional phase space in which you have kept xj and pj unchanged, right. So the remaining dimension is 2n minus 2. So whatever you need to do is in this dimension, provided you want to look at a fixed point like this one. So as a result, the stability subgroup of this is, what should be the case? The same analysis you will see, and this should be k n minus 1, right, because you will have to consider rotations in this 2 n minus 2 dimension, you will have to consider symplectic transformations in this 2 n minus 2 dimension, and then their intersection, which will give rise to k n minus 1. Okay. So, the point is that this is how you get rid of repetitions of action of elements of this. So, basically the point is that if I now look at the coset, so k n divided by k n minus 1, okay. So, this which is called the coset. So, coset in the sense that this can get rid of these fixed points. So, this will be actually your S 2 n minus 1. So, this is basically tells you that you forget about those transformations from k n which will keep elements of S 2 n minus 1 intact, they should not change, and rest of the things what you take is basically this one. Okay. So, this tells you that now why do you want to get rid of such elements? What is the idea? Idea is that I want to figure out those elements of k n which act kind of non trivially. So, this kind of action that which will take which does not change these x j and p j, I will not consider that, those are not of my interest. Okay. So, what we need to look at is this coset space which is k n by k n minus 1 and which is actually your S 2 n. In fact, you can also prove that because we are dealing with this 2 n minus 2, again as earlier I said that the generators of this the maximal compact subgroup of now S p 2 n minus 2 and r, and what is that? This is u of n minus 1. In the case of S p 2 n r it was u n, now it is u n minus 1, right. So, what you can also argue that this is nothing but this coset space u n by u of n minus 1. Okay. So, yeah, so this is basically it tells you that what sort of symplectic transformations you should consider from this k n which will not change this S 2 n. So, which will take unit sphere to unit sphere, right. So, this is the you should think about it little bit, a bit of group theory will be required here to understand this thing. So, basically it tells you that, so what we are looking for is those elements of this k n which should not change this S 2 n minus 1, the structure of S 2 n minus 1 and this unit sphere in 2 n dimension. And if I look at it, it tells me that these cosets are basically if you figure out the transformations from this coset or transformation from this coset, then that will do the job. Okay. So,
So you originally started this discussion with asking whether any element of Kn can transfer a vector in this unit surface
Hmm.
2 n minus 1. So to any other vector.
yes. Yes. So, what we have seen is that under the action of SO2n. So, this is a transitive action on S2n minus 1, is that clear? That is what I said, that action of SO2n on S2n minus 1 is transitive, transitive in the sense that this is equal to this. Okay. Is it clear or no? Is that okay, right? Now, what I want is what is the action of K n on. So, this is what I want, action of K n on S2n minus 1. Is it also transitive? This is what we want. Okay. So, in other words, what I want is the following, that if I take S E mu, this collection such that S belongs to A n, whether this is equal to S2n minus 1.
E mu we can choose to be
Anything that is up to you. So, this is what I have chosen, but this is up to you, you know. Of course, this has to be an element of S2n minus 1. Okay. So, the question is whether this action is also transitive.
I think it should be the case, right?
Why?
Because if we take E mu as 1 0 0 0,
Mm.
then x we can take, we have freedom to choose x and y given those constraints.
Yes.
So we only need to be concerned about the first column of x and y and whether it can represent a general vector, because it will transform that 1 0 0 to a general vector, first column of x and first column of minus first column of y. So, I think a general it should be possible to choose x and y such that the first column of x and first minus of first column of y is a general unit.
Yeah. So, you know, where is the problem? Problem is here this is a kind of 1-to-1 correspondence. Okay.
Yes.
This is 1-to-1 correspondence from any point, you know, any 2 points of S2n minus 1 you can connect it through an element.
Yes.
In the case of Kn, it is not 1-to-1 correspondence. Okay. See, this transitive action, it demands. So, basically why it is not 1-to-1 correspondence? Because of this kind, presence of this kind of elements which will not change xj and pj. Okay. So, what we want is to get rid of those kind of transformations, and that is why you need to do this cosetting. If you take transformation from this coset space, then this is a 1-to-1 transformation. Only when you take, you know, if you just take from here, that guarantee is not there.
But then, like we said that SO2n, the action is transitive, so that is 1-to-1.
1-to-1, yes.
But SO2n is a larger group than Kn, right? Because SO2n intersection something is Kn. So SO2n is larger than Kn.
Yes.
Now somehow when we are doing Kn, we are getting like many to 1. It's very strange.
Yeah. So,
If I take something smaller than SO2n that's contained within SO2n, that should only, like, you know, I mean, I would naively expect it would only cover a subspace of the sphere and not the whole sphere. But it seems here like it's covering the whole sphere multiple times, like there's repetition.
yeah. So, the thing is that so why do I need to get rid of this kind of transformations where, you know, this condition is satisfied? Okay. Let us say I do not want to get rid of such element of Kn. Okay. So, what happens then? Can I say that that this Kn also acts transit? So, basically the point is that I want to figure out the orbit. So, what I want is orbits of E mu under Kn, because if I look at the orbit, then and if I can figure out that collection of all those orbits will be equal to the S2n minus 1. Okay. So, there is a problem here. Problem is that if I look at here, I start from this point E mu, I look at its orbit under SO2n. Okay. So, the so I look for all the points x where it can go under any element of SO2n, okay, all these points. Okay. So, so by this way you can cover SO2n, right, is not it? You start from a fixed point and then keep on applying this arbitrary S, not
S2n minus.
SO2n, yes.
So you can vary the element chosen from SO2n to cover S2n minus.
S2n minus, sorry, S2n minus 1, yes, that you can do. Question is, can I do also the same thing under Kn?
But Kn is a subset, like
It is a kind of subset, yes, yes, yes,
set than SO2.
yes, yes, yes. So, that is the question, that can I do it under Kn also. Okay. Okay. So, how do I understand that? Okay, maybe I will have to be little more explicit. Let me see. So, let us take action of this x y minus y x on E mu. Okay. So, okay, it depends. So, let us say mu is less than equal to n, this is the first case, right. So, then what will happen to this? What will be this one?
Times the restricted E mu.
Yes.
The first entry. Second entry will be 0.
Yeah. So, basically
0 and the third entry will be minus y times restricted E mu.
Yeah. So, now, so what I want is if this remains unchanged, okay. So, then what happens? Yeah. So, how to look at this action? This is what can I say? So, basically my point is that let us say this is equal to E mu itself, it does not change. Okay. Now, look at here under SO2n, can similar thing happen?
Identity in that test.
Identity, forget, that is a trivial one. Identity will happen same thing here also.
So, full rotation 2 pi
Mm-hmm.
will be identity 1.
That is identity, yes.
Yeah, then everything outside this EU sector perpendicular rotation happening, non-trivial rotation happening in the perpendicular to E mu. But at E mu, nothing happening. Like block diagonal.
Rather like E mu is the axis along which the rotation is
Yes,
happening.
yes. So basically, my point is that if this happens with E mu, then this will also happen with E of, this is at, what is that called? I mean, basically the corresponding position here, how do you call it? E mu plus n or something? Something like this, okay? So this will also happen.
Yes.
Okay? Right. Now, where is the problem? If you take such matrices, then it does not change these vectors, right? Okay, and then the problem is that you cannot scan these S2n minus 1. Now, does it not also happen for SO2n?
That there are always two vectors which are not moving.
Yes.
That does not happen, right?
That does not happen?
That if E mu remains invariant, E mu plus n will also remain invariant. For general S, general rotation, that's not the case, right? No constraint.
No, but every rotation there should be, oh, okay, so there is only one axis which will remain invariant, okay? Yes.
In general.
In general, yeah, only one. But here it is, you have two such things. Okay?
Because of this x constraint.
Right.
X y minus.
And so, I mean, there may be some other vectors also which may be true, but at least for these two vectors, this is the case. Okay. So, basic thing is you will have to get rid of those transformations, which will, because otherwise it will not be transitive action. It will not scan these S2n minus 1. Right. So, basically what you should do, so therefore you need to get rid of this kind of transformations which will not change these vectors. Okay. And that how will you get rid of? That is what I said. This is basically your Kn, you coset it with n minus 1. And that is why we say that this is equal to S2n minus 1, and this is also same as un. Same argument you can apply here, because this is also the compact subgroup, maximal compact subgroup of this sp2nr. Yeah. So therefore, you need to get rid of this kind of transformations. Otherwise, it will not scan. It will not act transitively. Okay. Right. Okay. Good. So far so good. So therefore, you see that I mean, I can take this K modulo this cosetting for its transitive action on S2n minus 1, right? And why this is important? Because now what we want is a generic statement about squeezing. So we need a generic statement about squeezing. Okay, and What does it mean? So you know that under this action, because to me only interesting thing is Kn, right, because that will only give rise to the eigenvalues of the covariance matrix. I will not go beyond that. So if I take this Sxy, so this is an element of Kn. Of course, it satisfies this condition. I am not writing it. This XX transpose plus YY transpose is good identity, etc. So now I take this, right, and then what I want is I take this Jj and minimum over 1 less than equal to j less than equal to 2n. If this can turn out to be less than half, then I know that this corresponds to squeezing, right, quadratic squeezing. Because I said that you can go to the Williamson's diagonal form and then connect it with this. I mean, this is basically, this is the less than half means that your quadrature squeezing in this j direction. I mean the not quadrature squeezing. What is that called? Uncertainty in the j direction is less than half, and therefore this corresponds to squeezing, right? Okay. So what is this? This is basically your, how do I get this thing? This is your S x y. How to take this? This is Ej, right? Ej transpose gamma S xy. No, I think I may be doing wrong. How to write this? Okay, so what is this? This is basically this, and I mean, let me. So this is your this one, right? This Ej and this is Ej, right? Something like this. So in terms of this unit vector, how will I write it? Yeah, this is fine. So this is basically S xy transpose, then Ej, then transpose of this, then gamma, then x y transpose, then Ej, right? So this should be half minimum over all j. Is that clear? Because the jth entry is basically this one, right? Now, because of course Sxy is an element of this Kn, Sxy transpose is also element of Kn. That is not an issue, because okay. So now I want it to pose it as an eigenvalue problem. So in that case, or minimum eigenvalue problem. In that case, this should be an arbitrary element of S2n minus 1, right? Only then I can say that the minimum eigenvalue, so therefore, minimum eigenvalue of gamma is less than half, right? If I can show that this is the case, that what does it mean? It means that I take x, what should be this, transpose, yeah, x transpose gamma x, and then minimum over all such x. If I can prove that this is less than half, then of course this is also true, and that says that the minimum eigenvalue of gamma is less than half, right? Okay. So here I need to use this transitivity property of action of Kn on S2n minus 1. and so therefore you see that, so by varying this Sxy, I can take arbitrary element of S2n minus 1, right, because this also acts transitively, provided I do not take arbitrary element of Kn, but in this coset space. Okay. So, therefore, what it tells you is that this, so if minimum eigenvalue of gamma is less than half, okay, then yeah, so then quadratic squeezing, then a quadratic squeezing will achieve squeezing on gamma. When I say on gamma means you will have to look at the corresponding symplectic transformation. Okay. So, on gamma will achieve the canonical form. Canonical form means the diagonal form. Okay, the diagonal form. Right. Or maybe I should say in the opposite way, that yes. So, actually say, yeah. So, if minimum eigenvalue of gamma is less than half, then I can find out a quadrature squeezing to bring this gamma in a canonical form. Okay.
Where have you used the fact that it's less than half?
No, because less than half corresponds to squeezing, right?
Yeah.
Because less than half, this is what we are talking about. This has to be a squeezing.
But we have also shown that if it's not a squeezing, even then it can come to the diagonal.
It can come, yes. Because we are restricting ourselves into the canonical transformation, which can be generated by quadratic Hamiltonian. Okay. So, all the statements are related to those kind of Hamiltonian only. We cannot talk about anything other than that. Okay. Yeah. So, okay. So, therefore, I can, if I apply a symplectic transformation from this Kn, of course, modulo this Kn minus 1, then I can and if under that transformation this becomes diagonal, this gamma, then because not under every element of Kn a given covariance matrix will become diagonal. Okay, so there will be specific cases. So if it becomes diagonal, then I can talk about whether the squeezing happens or not. Okay. Is that clear? Let me repeat it again. So what I said is that if at all I can bring this covariance matrix into a diagonal form under application of entries from Kn, modulo this Kn minus 1, then whether squeezing happens, whether that transformation corresponds to squeezing or not, I can figure out by looking at the minimum eigenvalue of gamma. Is that okay? Yes or no?
It's a bit confusing.
It's a bit confusing. Okay.
But
So,
sir, I want but in the finally, it's not always possible to find a element for all these covariance matrices which will diagonalize.
exactly.
Unitary. So what we do in that case?
You will have to live with that. So point is that if I take a covariance matrix and if it is diagonalizable through an element of this k n, that means I can figure out its eigenvalues etc., then the corresponding symplectic transformation which has brought this gamma into the diagonal form, whether it corresponds to a squeezing or not, that can be decided by looking at its minimum eigenvalue. Yes, is that clear? Yes. Okay, good.
If it's not squeezing, then it's some other kind of unitary rotation.
Because we are dealing with only quadratic Hamiltonian, we have two things here. One is either it is a rotation which follows from this compact subgroup, or it is this non-compact generators. We do not have anything else because we are dealing with only quadratic Hamiltonian.
So if it's not squeezing, we find out that it's not squeezing, then what it is?
Oh, if it is not squeezing, okay, then you know that it cannot be achieved by a quadratic Hamiltonian, which we have considered. Okay, it may be something else, but it is not achievable by a quadratic Hamiltonian. Okay, so that is the only thing we can talk about. I mean, there may be some higher order Hamiltonian with using which you can diagonalize and all those things, but those are not our concern for the time being, because for the time being we want to concentrate on transformations which are Gaussianity preserving. So, Gaussian state will go to Gaussian. We do not want to go into something else. Okay. I mean, it may be required later, but not for the time being. Okay. So, is this clear? I hope this is clear now. Eh? So, therefore, what it tells me is that it provides me a structure of this set K n, which contains these elements S x y, and then we can see that under the action of this S x y, if at all squeezing happens, and if it happens, I mean that will be decided by the eigenvalues of this gamma under such a transformation. Okay, good. So, what we do next? Next is that I will then what you can do, you can classify even further. So, you can classify this set, classifying in the sense that some sort of canonical forms you want to figure out from there. And why these canonical forms are important? Because this will help us to figure out what sort of transformation we should provide, squeezing, rotation, etc., etc. So, what we will do next time is we will group. So, basically we will classify these transformations into some simple canonical forms. One is called Gaussian canonical form, the other one is slightly general, the third one is even more general, but everything is kept in mind that the transformation should have this property of K n invariance. So, that we will talk later. So, basically what we are planning to do is to look for certain specific kind of these canonical transformations from this set, and which will ultimately, and why this is important, because when we will do this entanglement for Gaussian states, 2 mode, multi-mode, etc., these canonical transformations will be helpful. One canonical transformation will be basically, I told you in the case of single mode, that if you bring it to a thermostat where all the diagonal entries are same, then you can go to a form where diagonal entries are different, right, by applying squeezing. So, similar thing we want to do for higher dimension. So, basically what we will see is that ultimately we have not not very I mean not many such transformations, I mean which are canonical in form. One is this rotation that anyway we talked about with this compact subgroup. The other one is this the scaling transformation, and the third one is combinations of these two. And this is the case if I consider quadratic Hamiltonian. So, for quadratic Hamiltonian we only need these scaling transformation, namely squeezing and rotation and their combination, nothing more, nothing less. And with this we can in principle sort out this problem of entanglement for at least 2 mode Gaussian states. We can do that, we do not have to go anything else. Okay. Okay, good. So, let me stop here. Any question if you say? I think today's lecture is little bit unclear. You should look at this paper of Simon and other group theory papers, group theory literature. I think then it will be more clear, because this involves a bit of group theory, Okay, good.